of differentiation. We're going to look at a few of those. The first one is graphing of a function. Okay, number two, optimization, in which this is a huge branch of mathematics, as big as trig and geometry and algebra. Optimization, huge branch of mathematics. It deals with finding max and min. And number three, Newton's method. So these are the major ones here that we are going to look at. And this is the entire chapter 4. Okay, so we're going to start with graphing of a function, but we start with other things first. So in 4.1, we're going to talk about max min. I'm going to choose a function. You can choose a function if you'd like. So in 4.1, you can open on section 4.1, and let's choose a function, because there are a few items that I need to discuss, and then we'll choose other types of problems. Okay, so let's say I'm going to choose f of x. Feel free to choose from 4.1. F of x equals x to the third plus 6x squared minus 15x. Okay, so this is a function. Can anyone tell us what type?
Polynomial.
Very good. Thank you very much. It's a polynomial function. And we're asked to see whether the function has a max or min. Well, there is a big theory behind it. And the first step is find critical numbers. So when we talk about critical numbers, first of all, critical numbers come from two sources. It could be that f prime is equal to 0, and the solutions, x values, that make this happen will be, or are called, will be called critical numbers. Why? In a minute, I'll explain. But they can also, critical numbers can come from other second source, which is f prime of x being undefined at x values where f of x is defined. So critical numbers, one more time, can be determined from f prime of x being 0. I solve the equation. The solutions of this equation are called critical numbers. If this equation does not have solutions, the function doesn't necessarily is not necessarily void of critical numbers. I have to check the second option. If f prime is always defined, never undefined, then I will say this function has no critical numbers because I didn't find any solutions to solve this equation, and the first derivative is always defined. A function can have critical numbers coming from both sources, from none, or one or the other. Why are critical numbers important? Note, only critical numbers become max min. If a function does not have critical numbers, that function doesn't have max-min. Okay? If a function has critical numbers, there is no guarantee that it has max-min. If it doesn't have, let me write this down for you. If a function has no critical numbers, it's guaranteed not to have max-min. No critical numbers implies no max-min. Critical numbers implies f of x may have max-min. No guarantee. Something else has to happen. Okay, so first we have to determine the derivative in order to find, if you want here, critical numbers. So critical numbers come from one or the other, or both, or none, in other words. Okay, so here's our function. We find f prime of x. Can anyone give us f prime of x for this? You have to unmute yourselves. I muted you. So please unmute yourselves if you want to talk.
Yeah, that's going to be 3x squared plus 12x minus 15.
Very good. So the derivative is 3x squared plus 12x minus 15. And now I'm looking at two possibilities. Either f prime being undefined. Is this possible? Can this function be undefined?
No.
No. It's a polynomial function, is defined everywhere. So the other possibility is f prime of x being 0, which is 3x squared plus 12x minus 15 equals 0. And can anyone tell us what to do first?
Simplify the polynomial.
Divide the equation, both sides, by 3. So x squared plus 4x minus 5 equals 0. We are running a clean ship, in other words. Okay, can anyone tell us how to factor this?
X plus 5x minus 1.
Very good. So what are the options?
X equals negative 5 and x equals 1.
And this is definitely a critical number, and this is definitely another critical number. Will these turn into max-min? I don't know. They may. It's no guarantee. So this was step 1. We determined that this function has two critical numbers, negative 5 and 1. In step 2, we will start thinking of the following table again. So first row, f prime of x. The next row, f of x. What is the domain of this function? So I know what to put here. Can anyone give us a domain of this function?
Negative infinity to positive infinity.
Very good. Thank you, Jordan. Indeed. It's polynomial, all real numbers. Of course, I'm going to plug in negative 5 and 1 in the correct order. Of course, I'm going to write 0 under those numbers in the row for f prime. In this step, I study the sign of f prime. And you could say why. I will explain in a minute. Promise. So I look back at f prime, and now I know that this is 3, x plus 5, x minus 1. So one option would be to start plugging in numbers. I don't really like that unless we have to. So I know that this is a quadratic function that looks like this. And you can say, are you graphing the derivative? No, I'm not. I'm only talking about the sign. And I know that it crosses the x-axis, as we know, at negative 5 and 1. It's definitely positive outside the solutions and negative between the solutions. Or you plug in a number. If you plug in 0, you'll get negative. If you plug in 10, you will guarantee get positive. If you plug in negative 10, guaranteed you will get positive. Now the question is, why am I studying the sign of the derivative? What is it for? Why did I need all this? Okay, and let me explain now, and I'll come back to the table. So, why study the sign of f prime of x? Why bother with that? So let's take a look. Let's say I have a function. It's very clear that this is a relative max. And I see that the function is increasing before it gets to the relative max and decreasing after it gets to the relative max. So I have here slopes of tangents. I have here slopes of tangents. So when the function is increasing, what can you say about the first derivative?
As positive.
Yes. So when f prime is greater than 0, the function is increasing. What happens here at the relative max? Can anyone give us the slope of the tangent line at the relative max?
Yeah, it's going to be 0.
0.
Very good. Very good. Good. So now what we notice here is that a relative max requires a positive slope, a 0 slope, or undefined. What do you mean by undefined? So this means a 0 slope, and this means a slope that is undefined. Okay, so positive slope, 0 or undefined, and negative slope. And this is characteristic for a relative max. So positive, 0, negative, or positive, undefined, negative. This is characteristic for a relative max. Okay, obviously this is a relative min. The relative min or relative max is also local. Local or relative, they mean the same thing. We use them interchangeably. So obviously, what is the characteristic for a relative min? What sign of the derivative on this side?
Negative.
And then positive. So the typical situation is negative 0 or positive, and positive, negative or undefined and positive. This is characteristic for a relative or a local minimum.
When it's undefined, would that be like a hole or something?
No, the derivative is undefined. Okay, so sorry. So this is for the derivative. The function must be defined. The derivative can be undefined. This is a relative min, but the derivative is undefined. It's a corner.
Gotcha.
Negative, positive, but here the function must exist. So this is for f prime. Or something like this. This is a cusp. The derivative is undefined here. But the function is defined. And this will be a relative min. So that's...
Was there a third case where it's undefined too? I remember
yes, the vertical tangent.
Vertical tangent, okay.
Yes. So in all these situations, the function must exist. If the function doesn't exist, then how can it have a max or a min? So the discussion here is for the derivative. Very good question.